Well, I think it should be recorded. Yes, I should. Anyway, welcome everybody. Welcome. You may be wondering, where's Chris? Well, Chris, our president, Chris Gunther, is doing some continuing education. He asked me, my name is Mark Pankratz. I am the vice president of the chapter. He asked me to take over as far as hosting it. And so here I am. And thanks again. I guess I should start with, and I hesitate to do this on Zoom because I know it kind of lacks some, shall we say, human interaction. But if there's anyone out there that would like to say hello, you're new and you'd like to make your presence known, please feel free to do so. I don't know, Larry, is there anybody there that you don't recognize? Probably not.
Alex.
Anyway, I'll move.
Johnson?
Yeah, anybody? If you, and don't feel pressured. If not, we'll continue. That being said, as Chris normally does, we'll get some updates here. Has anyone got anything to talk about as far as builder reports? Anything that's going on that they'd like to share as far as building, flying, whatever? We'll take a minute if you'd like to share. If not, you're right. We'll wait, because generally speaking, let's face it, we'd rather do this in person. But anyway, speaking of back in person, and try to understand, we don't like doing these Zoom things. It's just we go by a number of things, of course, infection rates, but especially if there's a mask mandate going on in Frederick, we take cues from that. We do. But we're really hoping to get back into in-person in March, and that is currently the plan. And so you'll see more as far as confirming that or not as that date approaches, but certainly that is our hope. Does anyone like to share anything as far as the veterans build and that update?
Oh, yeah.
I guess I might be the only person on it right now. It's going really well, really quickly. We've got a large part of, well, the tail is done, except for the vertical stabilizer, which for reasons understood is part of the finish kit, go figure. But we've also done the, what we've been working on is the right wing, and it's very much coming along. It's been the whole bottom skins and everything have been riveted in place, and this thing goes together pretty quickly. So it's going well, and the veterans are having a good time, and it's great. Yeah,
sounds great. Sounds great. You've seen a number of airplanes. You guys pretty relatively impressed with Zenith and the kind of the components, the quality of the materials?
The match drilling of the parts, how Zenith says if the holes don't line up, you're doing something wrong. That seems to be really true. That's the positive. The negative is that the directions and the plans don't always agree with each other. And there are parts of it that are kind of vague, but I guess that's probably true of a lot of, I've never built anything else, so, I don't know.
No, I can vouch for that. That happens with vans as well. Absolutely.
But we figure it out. Sometimes it takes some head scratching to get it done, but
yeah,
we figure it out.
It's all part of the fun.
Yep. Oh, well, there's two of our veterans just showed up. Alex
Excellent.
And Scott can tell you more, maybe.
Guys, do you have any comments on the build?
When I can get there, I love it. I mean, this is, I do something, I mean, it's like I have some background, but I don't have it in hands-on. And this is amazing stuff. This is really fun.
Yeah, and I'm amazed at how well things line up most of the time. There's hiccups now and then, and yeah, definitely there's a little bit of intuition required to get through some aspects of the instructions. You know, like one thing we're looking at right now on the right wing is there are pictures with no fuel tank installed in the wing. And then in the next page, the tank is there, and you're like, okay, well, I guess it's time to install the tank. I mean, that's probably the most extreme example, but yeah, you got to be careful with what you're doing. But you know, since you put it together, Clico and drill it and take it apart again, you got a couple of shots at it to make sure you know what you're doing.
Well, and another thing I've learned, especially building a metal airplane, is metal's forgiving. If you mess it up, you just order another part because it's relatively cheap just to get another part and replace it.
Yeah.
Anyway, no, thanks for sharing. We're excited about it. And I know most of you probably know that the reason that model was selected was for its ease of getting in and out, for its ability to, has anyone talked about modifying any of the, right? If somebody had a disability and needed some form of controls that was different than the original plans, I don't suppose any of that's come up yet.
The original reservation of the kit included that. There are modifications available, but as it turned out, none of our veterans need that. So that part of the order was canceled, at least for the time being. Yeah.
Yep, makes sense. Well, great. Ernie, you got a little COVID going on there?
No, no.
Sorry, I couldn't resist. Anyone else want to comment on the veterans or other builds or flying experiences? Okay. All right. In that case, I'm going to jump right into introducing our speaker. Somebody I'm really excited about hearing from, having read the book Cosmos recently, and that was from an earlier presentation from John Varljan, who also spoke on space stuff. But anyway, Tom Comeau. Tom, I hope I'm pronouncing that correctly.
Comeau, rhymes with bureau.
Thank you. What an impressive resume. So he's a pilot, and he's building a Fisher Flying R-80. This is a Tiger Moth. That's what you see in the background is the structure of that wing. Anyway, he's a contractor for NASA. He's been doing this for a long time. His title is currently the Assistant Wavefront Operations Scientist and Principal Computer Scientist for the telescopes team at the Space Telescope Science Institute.
That's really impressive when you say it.
Well, it is impressive, and yeah, that's really cool. Anyway, this guy operates the James Webb Telescope, folks, and he is here to tell us all about it, give us the latest. Tom, I'm pumped about hearing about it. Thanks so much for doing this, and it's all yours.
Okay. I need screen sharing. I think that's a Larry problem.
That's a Larry issue. He's on it. There we go.
You got it.
Excellent.
I almost got it. I cannot start screen sharing while the other participant is sharing. I think you started yours, Larry.
Probably so. You should be good now.
Ah, here we go. All right.
Bingo.
There we go. All right, so I'm going to show some slides, and I'm going to, where's my little thing that says do slides? I'm a little confused.
I might be able to help you. Hold on. You're right.
Slideshow.
There we
Play
go.
from start. There we go.
There we
All
go.
right. Okay. Let me get rid of this part over here. All right. I'm going to show some slides and then show a little movie and then talk a little bit about what we're going to do with James Webb once we're commissioned. JWST is this monster telescope. It's the most expensive telescope ever built. So the current price tag is about $10 billion. It's the successor to Hubble, but it's not really a replacement for Hubble. Hubble is actually still going strong. I came to the Institute a couple years before Hubble was launched and worked on that for a couple decades, and then started working on JWST in 2007. Was away from the project for a little bit, came back to help out for one day, and that turned into months of testing at Goddard and then at JSC, and then away from operations to get the observatory focused. So this is where I work. This is on the Johns Hopkins University campus. This was taken Christmas Eve, the night before launch. And you can see that we're all lit up, but there is that little notice in the middle on the door there that's about COVID. And so COVID has really made things a little more difficult for us. There's fewer people in the building than we expected. There's a lot less celebration going on because everybody's masked. And it's very annoying because I get tested every day. So I'm very sure I don't have COVID as of early this morning. This is the sort of office where I work. If you look closely, you can see this was taken a week after launch on mission day 7. I sit all the way over on the left. And when we're working, there's a whole bunch of people there. There's people from Goddard. There's other people from the Institute. There's people from Ball Aerospace. And there's people from Northrop who all work together to figure out where we are and how to get aligned. There are 2 blogs that you might find interesting. The one on the left is the build behind me. That's 728 Tango Charlie, an R-80 Tiger Moth. And we'll come back to that really red looking picture there in the lower right of that side. On the right side is the blog for JWST. We just a few days ago arrived at L2 and got inserted into our orbit. And literally last night, overnight, we finished doing our first images of our first target to start the alignment process. So keep an eye on those 2 blogs to see how I'm doing at home and how I'm doing at work. This is JWST. It's gigantic. The sun shield at the bottom, or sort of actually in the middle, the spacecraft itself is at the bottom. The sun shield is literally the size of a tennis court. In fact, they set it up on a tennis court out at Redondo Beach, the model of it, the full-scale model of it. The part that's interesting to me is the gold part. Yes, our mirrors are gold-plated. There are 18 segments that point at a gold-plated secondary that reflect the light back into that black tube in the middle that goes in, that gets bounced around a couple more times and then goes back into ISOM, which is behind the mirror. That's the integrated science instrument module. That's where the cameras and the spectrographs are. This is the pre-encapsulation photo. So you go from completely unfolded to completely folded. It's still big. This is as big as we could make it because the fairing there on the left, and there's also one on the right for somebody else, but the fairing there on the left that we're going to go into is the largest fairing available. That's the Ariane 5 fairing. It's just a little bit larger than the Falcon 9 fairing and the Atlas fairing. So we picked the biggest fairing we could find, and you still can't get a telescope as big as Webb into it without folding it up like a little origami thing. The last time I was with the telescope is the picture on the left. I'm standing in the clean room at Goddard just before it was shipped to JSC for testing. The picture on the right is a couple years later at Redondo Beach. That's the last time I saw Webb. And you can see there that while the side wings on the mirror are folded back, the sun shield is completely unfolded, and they're actually the guy on the man lift there is looking for tears in the sun shield, and fortunately he didn't find any in that inspection. There had been a couple of attempts to do a deploy where there had been small tears that they had to tape up. So JWST has gone all over the country. Before it got shipped to JSC, I did have the chance to take my daughter down and let her look at it. That's right at the end of the program as they're preparing to put it in a shipping container. They're doing some final inspections and cleanings. And that's me on the right getting into my bunny suit to get prepared to go in. I have to leave my phone outside, but it was interesting. You get into a bunny suit, not to protect you, but to protect the observatory. Finding a hair on a mirror or in an instrument would be a real mess. And so we get into this, and then after this, you get a static strap on. I don't think this is the same time, but if you ever get to see my watch, I have a Omega Speedmaster watch that actually broke on the turnover fixture because I was paying more attention to where the observatory was than where I was. And so I've got this crack in my crystal that somehow I just don't want to get fixed. We took the observatory down to Johnson Space Center to the same chamber that they tested the Apollo spacecraft in. So if you think about, you can put an entire Apollo spacecraft in this chamber. We were only able to fit the OTE part of the observatory in there. The sun shield is too big to fit in this chamber. And then we did a series of interferometric tests to get the observatory aligned using this laser light source at the top of the chamber that points down. We also had this, what we call the ASPA, the Aft Optical Subsystem Source Plate Assembly, which is, it shoots a bunch of lasers up at the secondary and then back down to the primary. And then it gets, it goes back, bounces back again and into the detectors. And so you get this, what we call the pass and a half testing. And we use that at JSC to align the observatory, but we don't have sources on the flight observatory. So we have to use ordinary stars. And I'll show you how we do that a little bit later. To get down to our operating temperature, which the instrument operating temperature is 25 Kelvin. The mirror operating temperature is about 40 Kelvin. That's some ridiculously low number. It's minus, I made a note here somewhere, minus 414 Fahrenheit. Except for the coolest thing in space. The coolest thing humans have ever put in space is MIRI, which will operate at 7 Kelvin. That's minus 447 degrees Fahrenheit. It uses a special cooler that gets down from 25 to 7 using a series of, well, heat pumps, basically, gas expanders. So, you know, airplanes are designed to operate over a fairly narrow temperature range, maybe 20 below, maybe, all the way up to maybe 100 above. The warm side of JWST is maybe 125 degrees Fahrenheit. The cold side, as I say, is minus 414. So we go over a very wide temperature range. The testing at JSC involved putting the whole optical telescope inside chamber A. The picture on the left is actually of the Pathfinder, which is just the center section of the OTE, not the full. I tried to find a good picture of the full OTE going in. It turns out that they're all ITAR. For some reason, the State Department classes JWST as a weapons system. It's, I think it's because of our infrared sensing capability. Anyway, the door on the right, which some of you saw as my background picture sometimes, is the chamber A door. The little black square below the NASA logo is the National Landmark, National Historic Landmark plaque. This is, we're very aware on the project of how much we benefit from the history of things like the Apollo program and the Hubble program and some of the European programs. We learned a lot from other people doing difficult things, and we're trying to do interesting things with JWST using all of the lessons we've learned from those programs. But the best part about JSC was the weather. While we were there, in fact, I went to bed the night before we were going to start doing a round of alignment. And this was the picture on my phone on the left. Hurricane Harvey was parked offshore, about to come in. The Chamber A building is actually 3 buildings. There's the tall building where Chamber A is. There's a shorter one where the Chamber B, where they test spacesuits, is. And then there's a control room that's actually in a separate building that's, all connected up. The seam between the Chamber A building and the control room building sprung a leak. And so it was actually raining inside the control room, which led to us having to sort of work inside a tent. You can see where the ceiling there got all discolored, but we stayed dry. We ended up having to put our computers up on 2x4s to keep them from getting wet. The people at the facility people at Johnson did a great job of getting the water under control, cleaned up, keeping us dry. And we did get the observatory aligned. I mean, that's the picture on the right there is a heat map of where there are aberrations in the mirror. If this were all a perfectly aligned mirror, you'd have one uniform color. The difficulty is that we were testing the mirror in a gravity environment. And those pink print through blobs that you see there are actually the actuators underneath the mirror that drive the mirror around. There's 6 actuators arranged in a hexapod configuration. And those actuators can drive the mirror to, there's a coarse stage and a fine stage. The coarse stage, a step is about, a rotation is about, it's just a screw, and a rotation is about 60 nanometers. But the fine stage has this little cam on it that moves up and down and gets you to about 4.5 nanometers. So we can align these mirrors very precisely. The goal for the flight article is 131 nanometers of wavefront error over the entire field. And we got down to 153 in this image, and we actually did a little better later on. But there is an issue that the segment on the far right there that looks like it's different from the others, it's got this extra little bit of distortion in the corner. It turns out that the segment was actually snagged on a piece of ground support equipment. And so it was pulling just a tiny bit on the segment. We won't have that problem in space because we don't have any ground support equipment in space. This is the last picture, the last really good picture we got of the observatory right after separation from the Ariane vehicle. This is the picture that we keep up in the wavefront office as our background. You can see sort of in the lower lower left there, there's 3 little things peeking out. Those are the star trackers that do the initial pointing of the observatory. And then we do a fine pointing with the fine guidance system. Near the lower left of the disk in the middle are the thrusters that were used to do the MCC1 burn. The Ariane people gave us an almost perfect deployment. They gave us very close to the upper limit of the specification. We didn't want them to push us too hard because we need to coast out to L2 and just barely get short of that. We don't want to go so far that we escape from Earth orbit, but we want to stay right at the limit of the Earth orbit. And Ariane gave us just a perfect push. And so, sorry, the initial burn we had to do for mid-course correction 1 was quite a bit shorter than we expected. And as a result, we had a mission requirement to operate JWST for 5 years and a goal of 10. And we have enough fuel on board because of that, because that first burn was so short, that that we now think we have more than 20 years of fuel on board. So JWST will be able to continue operating for probably more than 4 times its specification lifetime, which means that we'll be able to keep doing useful science into the 2040s. The gold thing on the right side there is the back side of the high gain antenna. That's how we communicate from the observatory back to Earth through the Deep Space Network. We have to do a handover between stations 3 times a day. And that gets us a whopping 2880 megabit downlink rate. So many of you will remember the 80s when you had to do dial-up modems. This is sort of a medium fast dial-up modem. And that's because we're a million miles away in the cold and the dark beyond the moon. The most encouraging thing we saw during the whole launch sequence, this is probably the last picture of JWST is anything larger than a single pixel anyone will ever get. But you can see the solar array was deployed there, which meant that we have power to operate the observatory. And it's already, by the time this picture was actually available to us, JWST was already the size of a pixel. And it's way less than a pixel now. But if you want to see it, if you have a decent telescope, just go point it away from the sun. Wherever the sun is, point your telescope directly away from that, and that's where you'll find JWST. Huh. Okay, so now that we've got it deployed and out at L2, this is the plan. This is the thing on the left is the simplified block diagram of how we do OTE alignment. And the thing on the right is what we were doing last night. I actually started yesterday afternoon, ran all through the night into today. When I left, we were doing the last of the top stripe there. And we're waiting for the data to download, but all indications are that this all went really well. Let's see what I want to say about the first row of boxes in this diagram are all done, and we're ready to start actually doing the initial alignment. This is the target that we're pointing at right now. If you the Big Dipper in Ursa Major, if you follow the top of the dipper off to the right about the same distance, 84406 HD 84406 is almost a naked eye target. If you are in a really dark place, like when I went out to Boulder to go to Ball, I would go up to Rocky Mountain National Park at night, and the stars were always spectacular. You could actually see the Milky Way. It's just about visible in an environment like that. Around here, a decent pair of binoculars, you should be able to find our star. And we spent the last 2 days staring at that star, and we'll keep doing that for a few more days as we start through the alignment process. All right, so now what I want to do is show you how alignment actually works. The first thing we do is, and this is from a simulation that Charles Lajoie did. Charles is the deputy wavefront operations scientist. Marshall Perrin is the principal wavefront operations scientist, and then there's 5 of us assistants. So there's 7 of us who rotate through running the show, as it were, to get alignment going. So focus sweep, we actually deliberately move the secondary mirror back and forth to try and find a best focus. And what we're looking for is small PSFs. You'll notice that we started out with kind of large PSFs, and as we swept through the focus, they got a little better. So when you sweep through 5 positions and you pick the one that looks closest to best, and that's where you set the secondary to start the focusing process. And you'll notice that that's supposed to be complete at launch plus 43 days. Today is launch day plus 40. So if we are anything, we're like a half a day ahead of schedule right now. After focus sweep, we do segment ID. And the way we do this is we move each segment just a little bit, just 100 pixels one at a time. And then once we've identified them all, we get them into what we call a Shack-Hartman array, which is this big, come on, you can get there, this big array that looks something like that. And the purpose of this is we can take some measurements and see how the segments point and get them into a nice regular array so that we can do global alignment. Global alignment moves the secondary around to identify first tip and tilt, but also the position of the secondary itself. If the secondary is off to one side, which in most of our simulations, it's usually not perfectly centered. If the secondary is off to one side, you kind of have to move it into the middle, try and get things closer to alignment. And this Shack-Hartman array is used the same way that if you've ever done, if you've ever looked in a box at your ophthalmologist or optometrist's office and you see a little picture of a balloon and it gets fuzzy for a moment, this is the exact same technique. You do a little bit of defocus and you can recover what the aberrations are that you need to correct. So once we've got that part done, we try and get all the spots stacked on one point. And you can see that we kind of go in and then we go back out again and then we stack, we do the fine stack. And we do that because the process of moving the segments around uses up what we call the fine range. The fine range is lets us set the position of the mirrors to within about 4.5 nanometers, but that doesn't let us go very far. We can only do about 10 nanometers of travel. Sorry, we can only do about 10 microns of travel total in the fine range. And so what we have to do is move things around in the coarse range, get back to the middle of the fine range, and then adjust things in the fine range. And so we do this multiple stacking process to get through that. So once we've got it all stacked, then we do a really weird thing. Oh, I missed it, darn. There we go. All right, so this is called coarse phasing, and coarse phasing is a neat trick. What we're looking for is the segments might not be quite the same distance from the secondary. In fact, they're almost always off by maybe 100 microns from being at the same distance from the secondary. And you can see a little bit, especially like in the very top one there's kind of a barber pole effect. And the size of that barber pole, the amplitude across the field tells you how far off you are, because what's really happening is the edge of the light wave, the light wave is actually wrapping around the edge of the segment and falling onto the next segment. And so the size of that barber pole and the frequency of the barber pole tells you what the height difference is between the two segments. And then you move both segments closer to each other in the direction of best focus. Then we unstack into a small array and we do a process called coarse MIMF, which you actually missed it. We reverse the array and move off to the corner again. And then we go back into the big Shack-Hartman image array, do another round of global alignment, stack up again, do another round of coarse phasing. Now, the first time we went through coarse phasing, we tried to get within 10 microns. The second time we do coarse phasing, we try and get within 1 micron. Then we do fine phasing. Oh, there's the coarse phasing. We did a round of coarse phasing to get closer, but. All right, so for fine phasing, we use a different technique. For coarse phasing and for global alignment, you move the secondary around. For fine phasing, what we do is we stick a special lens into the path of the beam that defocuses without having to move any other mechanisms. And so in this case, what you have here is 8 waves of defocus. So let's see, that's going to be 8.8-ish nanometers of defocus. And from that, you can do a mathematical trick where you take this image, you know what the actual physical construction of the segments is. And what you're trying to find is how far are you from that design construction. And so what you do is you take this image, you do a reverse Fourier transform on it. That gives you a real part and an imaginary part. You know the imaginary part can't be real, so you throw it away, and you make an estimate of what the point spread should be, what this image should look like, and subtract it from what it does look like, and that tells you how much error you have left. And you can then correct the position of the mirror based on that. It's I love being able to throw away imaginary stuff. So we get through fine phasing, then we go off and get into we do multi-field, and then we have to recover from that, which means another round through, and that's what you get at the end. You get an image of a PSF that it's a tiny PSF. It's the encircled energy on a single pixel should be really small. It should be we should have a very sharp image. We were able to get very close to this image here. This is about 80 nanometers of residual. We were able to get very close to that at JSC, and we think we should, without the effects of gravity, we should be able to do even better on orbit. But you can see that the plan for this is L plus 121 days. So we have a couple of months ahead of us of going through this process. It's a long, semi-boring process. In fact, the motto of the Wavefront team is boring and flexible. So we like to stay bored. Boredom is good. When things get exciting on orbit, that's never happiness making. All right, so I call this presentation "The Hidden Universe Awaits," and the reason for that is this picture right here. So the bottom picture there on the left is a Hubble picture, and it's really, it's a spectacular picture. It's really pretty, but it's full of dust and gas, and so you can't see what's behind it. When you use an infrared telescope, you can see what's behind it, and so you can see that there's more stars. There's a whole collection of things back there that you can't see in the optical, but you can see in the infrared. The other, and this is actually a pre-launch simulation using data from WISC-3, which is also an infrared instrument. But JWST is also a much larger aperture, and so the resolution for JWST is roughly equivalent to the optical resolution of Hubble, but in the infrared, which means that we can see literally back almost to the beginning of reionization. So we should be able to see back within a couple 100 million years of the start of the universe. And we'll be able to look at things in the solar system that are also interesting. So the Cycle 1 General Observer Program has a really broad array of science topics, from looking at comets in the main asteroid belt, looking at the composition of those comets as they're cruising around, in that band between Mars and Jupiter. We have enough resolution and enough sensitivity, because we have this gigantic mirror, that we can tell you, not only what's in the water that mostly composes comets, but what all the volatiles and impurities are that are in that water. At the other end, there's a very modestly named proposal called Characterizing the Large-Scale Structure of the Universe, the most important question in astronomy. And that looks at supernova in very old galaxies, galaxies that are probably the first galaxies ever formed. Will have supernova in their core. Those supernova are the first stars that you can individually image, and we should be able to do that with JWST. So as we get into the summer and the instrument commissioning picks up after, so we go through OTE commissioning, we expect to be done with that in late March or early April. And then there's a couple of months of the instruments doing their commissioning activities once we give them a decent, a decent star function, what we call a point spread function. It's if you point a star at any reasonable distance is a point in the sky. It has no it's just a single point, but the optics spread out that point, and the description of how it spreads out is called a point spread function. And what you want is a point spread function that's tiny, that's really compact, and has fairly small wings. Now, because it's, you can see in that last image from the movie that there's some artifacts that are diffraction spikes from the edges of the segments. Those are unavoidable. They're just when the light strikes the edge, it moves out in that little pattern, and that's you can deal with that in doing your analysis if it's really well characterized, and we should have it very well characterized indeed in a couple of months. So once that's all done, you'll see the start of the early release science, and that will include both some close targets. I don't know that there are solar system targets in the early release observation, but there are nearby stars. There's a search for exoplanets that will be going on using candidates from TESS and Kepler. And then there will be some very deep observations. I was at the Institute before the start of Hubble, and the thing that I remember most is one Christmas when it was really quiet, everybody was away, and the director of the Institute decided that he would point Hubble at a blank patch of sky. The field he selected only had 3 faint stars in it. And the idea was that if you just kept looking, you should see fainter objects. And that became the Hubble Deep Field. If you stare at that blank patch of sky long enough, there's thousands of galaxies. We're going to do the same sort of thing with JWST's instruments, and we expect to see some of the first galaxies that ever formed.
Wow.
And understand why they formed the way they did, and what that means for the ultimate fate of the universe. I mean, one of the big questions right now is what is dark matter and how does our dark energy work? Adam Rees, who won the Nobel Prize for his work with Hubble on dark energy, now thinks maybe dark energy isn't constant over the life of the universe. And so he's got a program on JWST to look for, is there a turnover in how dark energy behaves in the universe? And what does that mean for the ultimate fate of the universe? So this is an exciting time. I feel really privileged to be part of it. I would be excited, except that I really want to be bored. I don't want exciting things to happen with the observatory. I want it to be a nice, boring effort that gets us a really spectacular telescope for the science teams to work with. All right, that's my spiel. Any questions?
Who's got questions besides me?
I do.
I have a question.
Description of the program. I just had a question. I worked on the mid-course space experiment out of Johns Hopkins way back when, and we always had a problem with, tumbling and spacecraft stability.
Mm-hmm.
How are you managing that to the fine degree?
Yeah.
You have to.
Okay.
Nothing on target.
Yeah. So one of the things that we just went through in the past few days was this solar torque calibration. Since most of the time we're just using reaction wheels to point the observatory. And the thing that pushes us off is solar torque. That big sun shield acts like, a sail. Well, it doesn't act like a sail, it is a sail. And so photon pressure on the sail will drive us a little bit out, but it's been extremely well behaved. The total momentum buildup has been small. And we've done momentum unloads on a semi-regular basis. We did more of them during deployment when we were a little bit asymmetric. But the engineers at Northrop did a great job of figuring out things like exactly where there's a flap on the back of the sun shield to try and balance the momentum. They seem to have really nailed that position. And the reaction wheels are extremely well behaved. We have 6 reaction wheels. This is really twice as many as we need. and they run at rates that are entirely reasonable. We had planned to do a momentum upload before the first set of observations, and we didn't need to.
Wow.
So things have been great. Momentum unloads are the thing that uses fuel, that and station keeping burns, and like the Ariane experience that we had, the first station keeping burn has already been canceled because we're in such a great, nice, smooth orbit, and so we expect to have plenty of fuel for many, many years.
Well, good luck.
Yeah.
It has a long service life.
Yeah. I heard another one out there.
Can you hear me?
Yep.
Well, I was wondering how big is L2? With mainly the question of, do you have to do anything to keep from colliding with other people or other machines that are in L2?
Yeah, so there's a couple other observatories that are out there. It's a big space. We're in a long orbit. It actually is I think it's a 180-day orbit for us to get around L2. So we're not sitting right on L2. We kind of creep up toward it, and we're in what's called a Lissajous orbit, which is we kind of circle around the L2 point. And yeah, there are a couple others, but they're in slightly different orbits, and we don't come into contact with them. We don't get close to them at all.
Great, thank you.
And the long term, so eventually JWST will not work anymore, or will run out of fuel. And when that happens, we'll move it out of the L2 region into a heliocentric orbit.
You nice guys.
Yeah, NASA's required to have a disposal plan for everything.
Great. This is a wonderful experience to hear what you've talked about. It's
Thanks.
fantastic.
Now, I don't understand L2 per se, but I'm guessing this is an orbit that's further out and keeps you away from like all the space junk and such. Is that correct?
Yeah, so L2 is a position that's about 1 million miles further out from the sun than the Earth. So it's out beyond the moon. So the moon's about 250,000 miles away. This is 4 times that. And what happens is that you can get out close to there, and rather than getting into a into a sun's orbit, you can stay in Earth orbit, but you can kind of get stuck out there, sort of wandering around the L2 area. It's the additional gravity from the sun and the moon keeps you positioned out behind the Earth. And yeah, so when the observatory goes into what we call safe haven, there's a little device on the bottom of the observatory. It's the simplest sort of stupid pinhole camera. It's the dumbest thing on the observatory. All it does is it tries to keep the sun centered in that camera. So we're always, when we're in that mode, we just point the bottom of the observatory at the sun, and that keeps the sun shield aligned, that keeps the OTE on the cold side. When we're not in that situation, we kind of roll and pitch around a little bit. We can yaw all we want. We can point the yaw axis in any direction we want, but roll and pitch, we're limited in how much we can do to keep the sun off of the OTE. But yeah, the L2 it's cold and it's dark, and the Earth and the moon and the sun, which are so it's moon, Earth, sun, are the 3 brightest things in the sky for JWST, and they're all behind the sun shield. And it's away from any other. So Hubble has been hit repeatedly by little bits of space junk. There's a big gouge, it's literally that big around in one of the solar arrays where it got hit by a paint chip. And the environment for HST is a lot warmer. It's almost room temperature in the aft end of Hubble, but on JWST, it's cold and it's dark, and that's what we want. The background is really low, and it should be fantastic.
So, hey, I have several questions. This info we're going to get, do we share this, for example, with other nations?
So JWST is itself a consortium effort. The Canadians provided the fine guiding system and part of the nearest instrument. The Europeans provided the launch vehicle and the optical bench for the mid-infrared instrument, and a bunch of other components for the other instruments. So this is a multinational effort. NASA's writing the biggest check, but an Ariane launch is not cheap. It's several $100 million, and we got it for free in exchange for having to go to Kourou to do the launch. And so the data will be available to anybody who wants to look at it about a year after it's taken. So there's an exclusive use period for the investigator who proposes the science. Now, things like the early release science and some kinds of survey, the data is available sooner, either after 6 months, or for the early release stuff, it'll be available immediately. You can go to mass.stsci.edu and download all the stuff you want.
Huh.
Not today, but you can go to mass.stsci.edu today and download an awful lot of Hubble data. All but the most current stuff is available on that's the Mikulski Archive for Space Telescopes. And you can get all that data is publicly available, except for that exclusive use period in the first year.
So some of what there is, some bits of this are classified, I presume.
No. So there are parts of it that are restricted under the International Trafficking in Arms Regulations or the Export Access Restrictions Regulations. All of that is related to the details of the design of the spacecraft interfaces and certain pieces of the infrared sensors. But for the most part, I can't go to China without having to talk to a security officer. I can't go to, it's Syria, Bangladesh. There's a Cuba. There's a list of like 13 countries that I have to check in with a security officer before I go there. But for the most part, all the information is publicly available. There is one secret, which I don't know, which is there's this authentication key that you use to control commanding of the spacecraft. You would need both a very large satellite dish and this encryption key in order to take control of JWST away from us. There's only a handful of people who know that encryption key.
Okay.
And it would be interesting to try to crack that, but I think unproductive. But yeah, there's not a lot of, there are some proprietary information. The details of how the star trackers work are they're covered under a trade secret agreement with NASA, but it's little technical details about how to build those things and what their process is for building them that gives them a commercial advantage. It's not a classification problem.
The only type of image that James Webb will do is infrared, correct?
Yeah, that's right. So we're just below the visible. The upper end is just below visible. You might be able to get just a little bit into the red. MIRI is the mid-infrared is a lot more into the infrared than anything that's currently flying. So Hubble covers from the ultraviolet. In fact, Hubble has the only general purpose ultraviolet spectrograph in the world is on Hubble. That's the cosmic origin spectrograph. But it's mostly optical and then into the infrared a little bit. MIRI is quite a bit further into the infrared. And that's an advantage when you're looking at old targets, because as you get further away, the light from those distant objects gets redder and redder because space is expanding. And so those light waves get pulled apart. And so going deep into the infrared lets us see the most distant targets in the universe, the oldest things in the universe, the things that are furthest away. A telescope is a time machine. And so we can see further back in time, right up to the first galaxies, and maybe even right up to reionization, the first stars.
Right. The assumption was from the Big Bang, everything emanated from that central point.
Yeah.
Us being part of that, and that's why
you
can go back in time. Okay.
Yeah. And there's some caveats about inhomogeneities in the early universe, but the other thing is that the thing that got Adam his Nobel Prize is not only is it expanding, it's expanding faster as it expands. And the driver for that is dark energy, and we don't know what that is. But there are multiple programs, including one of Adam's programs, to try and investigate what that is and how it behaves.
And you're talking about black holes, right?
No, so black holes are a form of dark matter. They're not really, because you can identify them. You can tell how they interact with the environment around them. Dark energy is something much weirder. It's an energy that's actually pushing the fabric of space apart.
Huh. And it can be seen?
You can see its effects on gravity, but you can't actually see dark energy itself.
No. Yep.
But you can see its effects on gravity. Gravity is the weakest and most powerful force in the universe.
Will James Webb help with maybe identifying if there's a killer meteor inbound to Earth?
So we'll do some surveys of the Oort cloud, which will give you an idea of something that's, flying in from the outer solar system. But we're a terrible survey instrument. We have this pencil thin area of the sky that we cover. The Roman Space Telescope, which is coming along a few years later, that a lot of the people I work with are also involved in, is a survey instrument, and that will give you a chance to see fast moving objects coming from the far reaches of the solar system.
Okay.
So yeah, watch for the Nancy Grace Roman Telescope. That's I think their launch date is currently 2026 or 2027.
Is that NASA as well?
Yeah, that's NASA, and the Institute will be involved in operating that as well.
Cool.
I work with a bunch of people on the data management side who they're spending all their time working on Roman. They view me as an annoyance for wanting data right now. They have this other stuff they want to work on.
Fascinating. Anybody else?
Yeah, I have a question. When do you think we'll get our first pictures?
June. Yep. Maybe early June if things continue to go well. And those will be the early release observations. The pictures that we're getting right now, they're engineering pictures. They're not a star doesn't look like a single point. It looks like 18 points plus a bunch of crap. The instruments are still very warm. And so we see a bunch of, odd effects from not being down at their operating temperature. They're almost at 100K right now. So they're 4 times their operating temperature. And so there's a bunch of work that has to be done to get the instruments tuned up, get the telescope tuned up, like I showed, in order to make it look like a real astronomical image. And so the first astronomical images, they'll probably be released in a bunch in early June.
Do you know if there's a plan to find Planet 9?
There are certainly plans to look in the outer area of the solar system for planets. How many planets there are in the solar system is sort of it's almost an aesthetic question now. It's not 9. It's either 8 if you're using the IAU definition, or it's about 43 if you use some other definitions. And we think 43 planets is too many for kids to memorize in school. So.
Yeah, I heard they were talking about naming a couple of the moons of Jupiter planets.
Yeah, so that doesn't, I would not think that would be a reasonable thing to do because those moons orbit Jupiter. But there are a bunch of similarly sized objects in, the Jovian, Neptunian area in the outer asteroid belt that are certainly big enough that, like Ceres is a planet, right? It's almost as big as Pluto. So you could reasonably call that a planet. But once you do that, once you change the definition so that anything that's basically round, now there's a whole bunch of objects, including a bunch of them, way out beyond the orbit of Pluto,
right?
That look like planets. So,
right now, what is the propellant on James Webb?
It's it's a hypergolic So it's UDM something. It's hydrazine and whatever the standard oxidizer is for hydrazine, which is in my head, but I can't remember right now.
Right. You just mix them and they combust basically.
Yes, and we only use that. We only use both parts for the station keeping maneuvers because it gives you too much impulse for a momentum unload. So the momentum unloads are all done with just hydrazine as a monopropellant. Goes over a catalytic bed to liberate the hydrazine to give you a lower level of thrust.
Now, you think there's any way they can extend the life of James Webb by setting out another satellite to support it or anything?
So there is a refill fixture and there is a docking target near that refill fixture. So in principle, you could do that. I don't know that anybody's working on that, especially now, since it looks like, 20 years from now, these instruments are going to be old and they're going to have a lot of cosmic ray damage and they're going to be relatively less interesting. It's not like Hubble where we can replace the instruments. The great thing about Hubble, the thing that kept Hubble productive for so long was that you could pull the high resolution spectrograph out and put a different spectrograph in. You could pull out WISPIC2 and put WISC3 in with better electronics, better optics, larger detectors. We won't be able to do that with Webb. And the plan is too strong a word. What the decadal survey recommended was that you build a really big mirror, that you build something in the 30-meter class. Probably won't end up being that big, but build something really quite large with the latest generation of instrumentation and especially coronagraphs. There are coronagraphs on JWST for looking at the coronagraphs. Cool. What you do is you take you point at a bright thing and then you put a blocker in front of the bright thing and you try and figure out what just barely peeks out beyond the edge of that blocker. And that's how you find exoplanets. You cover the star and you look for this little thing that's reflecting the star just outside the coronagraph. The next generation of coronagraphs, the kind of stuff that will go on the large optical UV infrared observatory that's sort of in the definition phase right now, are going to be spectacularly good. You'll be able to get ridiculously great contrast levels far beyond what we can do today using a combination of adaptive optics and new techniques for coronagraphy.
Now that's LUVOIR, right?
Well, so the decadal survey very carefully avoided saying LUVOIR or its competitor, which is HABEX, which is for the Habitable Planet Explorer. They basically said, take ideas from both of these and make one big, really cool observatory.
Now, do you think they'll make one big observatory? Would they send out 24 small ones?
Yeah, so in astronomy now, aperture is everything. The size of the mirror determines how much light you get and to some extent how well you can focus it. It's perversely easier to focus a really big mirror. So if you had there's 18 segments on JWST. A segmented telescope is an interferometer with a common secondary. And so it's actually easier as you get to more and more segments to get a really good focus. The math actually gets nasty, but there's some techniques you can use to get it to work really well. And so, that argues for making a really big mirror so that you can collect a whole lot of light. You can see very deep and you can see at very high resolutions. And so I think they will build we'll build as big a mirror as we can launch. And the JWST experience, because the deployments went so smoothly, has given everybody a lot of confidence that you can build big deployable structures and then autonomously deploy them. So I think we'll build something really big, but that'll be after I retire and go on to flying full time.
Now, this is probably out of your realm, but do you know anything about the telescope that SpaceX has been asked to
No.
build or anything like that? No.
No, I don't know anything about it.
Cool. Thank you.
Nobody else? Well, Tom, that was outstanding. By the way, I failed to mention that Tom, as I think most of us know, is our VMC coordinator. And so we are just so fortunate to have somebody of this caliber doing what he does for the chapter. Thank you, Tom. I really want to just hats off. And hopefully down the road, we can maybe hear some more from you, maybe some images and so forth, because I do think fascinating subject. So thanks for sharing. We really appreciate it.
Sure. I do want to plug VMC Club this month is the week after IMC Club because of the quirk of the calendar. So it's a week later than you might have expected. But let's see, what are we talking about? I don't remember what I'm talking about this month.
Okay.
There'll be a spans notice, and I'll post in all the usual places what we're going to talk about.
Great, great. All right. Anyone else have anything else to add for the good of the chapter before we convene? If not, thanks for being here. Tom, thank you again. Everybody,
Thanks for
enjoy
filling in,
your
Mark.
evening.
Thanks, Tom.
Yep. We really appreciate it, Tom. We'll be
Thanks,
in touch.
Tom.
I'm going to go to bed now.
Thank you, Tom.
Well deserved. Okay.
Good
night.
night, everybody.
Night.